Welcome to G Fun Facts Online. Today we're unraveling one of medicine's greatest and most heartbreaking mysteries, Alzheimer's disease. For over a century, this disease has been a relentless thief of memory, personality, and life itself. It currently affects an estimated 57 million people worldwide, a number projected to skyrocket in the coming decades. This isn't just a story about a disease. It's the story of a monumental scientific quest, a journey through groundbreaking discoveries, devastating failures, and the unyielding hope that we are finally entering a new era of understanding and treatment. The story begins in 1906 with a German psychiatrist named Dr. Alois Alzheimer. He was treating a patient, Auguste Dieter, a woman in her early 50s with a baffling condition. She suffered from profound memory loss, paranoia, and unpredictable behavior. When she passed away, Dr. Alzheimer examined her brain and found something he'd never seen before. It had shrunk dramatically, and under his microscope, he saw two strange structures. There were dense, sticky clumps outside the nerve cells, and tangled bundles of fibers within them. These would come to be known as plaques and tangles, the defining hallmarks of the disease that would later bear his name. For decades, Alzheimer's was considered a rare form of presenile dementia, a scientific curiosity. That all changed in the 1970s, when researchers established that the very same plaques and tangles were present in many older adults suffering from dementia. Suddenly, Alzheimer's wasn't a rare disorder anymore. It was revealed to be the most common cause of dementia and a massive public health crisis. This realization ignited the modern era of Alzheimer's research. The first major theory to emerge was the, quote, cholinergic hypothesis in the late 70s, which pointed to a deficit in acetylcholine, a chemical messenger vital for memory. This led to our first generation of drugs, like cholinesterase inhibitors, which boost acetylcholine levels. They can help with symptoms for a while, but they do nothing to stop the underlying death of brain cells. It's like patching a leaking dam with chewing gum. The real seismic shift came in the 1980s and 90s. In 1984, scientists finally identified the main ingredient of those sticky clumps Dr. Alzheimer saw, a protein fragment called amyloid beta. Soon after, they identified the protein that makes up the tangles, tau. The case for amyloid being the primary culprit grew even stronger with a key genetic clue. People with Down syndrome, who have an extra copy of chromosome 21, often develop early-onset Alzheimer's. It turns out, the gene that produces the precursor protein for amyloid beta is located on that very chromosome. More amyloid production seemed to equal Alzheimer's. This all culminated in the formulation of the amyloid cascade hypothesis in the early 1990s. It was an elegant and compelling story. It proposed that the abnormal accumulation of amyloid beta is the first domino to fall. This triggers a chain reaction, leading to the formation of toxic tau tangles, widespread brain inflammation, the death of neurons, and finally, dementia. This theory became the central dogma of Alzheimer's research for more than 2 decades, channeling billions of dollars and the brightest minds toward a single, unified goal: stop amyloid. The strategy seemed foolproof. If amyloid causes the disease, then getting rid of it should be the cure. What followed, however, was a clinical catastrophe, often called the graveyard of failed trials. Between 2002 and 2012, the failure rate for new Alzheimer's drugs was a staggering 99.6%. Drug after drug, designed to reduce, remove, or prevent amyloid plaques, failed to show any meaningful benefit for patients. High-profile antibody treatments like solanezumab and gantenerumab AB successfully cleared amyloid from the brain, but patients' cognitive decline continued unabated. This long, painful string of failures forced a difficult reckoning within the scientific community. Cracks began to appear in the amyloid hypothesis. For one, there was the plaque cognition mismatch. Autopsies revealed that many older adults had brains full of amyloid plaques but had shown no signs of dementia in life. Conversely, some people with severe Alzheimer's had a surprisingly low plaque burden. the link between the amount of plaque and the severity of symptoms was surprisingly weak. Then there was the timing problem. We learned that amyloid plaques begin accumulating in the brain 15 to 20 years before the first symptoms of memory loss even appear. This raised a critical question. Were the trials simply intervening too late? By the time a person has dementia, the damage cascade might be so advanced and widespread that removing the initial trigger, amyloid, is like clearing rubble from a building after it has already collapsed. The situation was further complicated in 2022 by allegations that a highly influential 2006 study, which seemed to prove a direct link between a specific type of amyloid and memory loss in rats, may have contained manipulated images. While this didn't invalidate the entire body of amyloid research, it fueled growing skepticism about the theory's dominance. It became clear that while amyloid is undeniably part of the Alzheimer's story, it isn't the whole story. The reality of the disease is far messier than a simple, linear cascade. This has pushed us into a post-amyloid era, not one that discards amyloid, but one that places it within a much broader and more intricate biological web. So if it's not just amyloid, what else is going on in the Alzheimer's brain? It turns out there are several pathological culprits working in concert. Let's start with the other hallmark Dr. Alzheimer saw, the tangles made of the protein tau. In a healthy neuron, tau acts like railroad ties, stabilizing the microtubule tracks that form the cell's internal transport system, which moves nutrients and other essential molecules around. In Alzheimer's disease, tau becomes abnormal and misshapen. It detaches from the tracks and clumps together into insoluble tangles inside the cell. This causes the entire transport system to collapse, disrupting communication and ultimately starving the neuron to death. Crucially, unlike amyloid plaques, the location and density of tau tangles in the brain correlate very strongly with the progression of cognitive decline. This suggests that tau pathology might be a more direct driver of the symptoms we actually see. It's now thought that amyloid accumulation might act as a trigger that accelerates the spread of this toxic tau throughout the brain. Another major player is neuroinflammation, or as some call it, a fire in the brain. For years, inflammation was seen as just a side effect of the damage from plaques and tangles, but we now know it's a key driver of the disease itself. The brain has its own immune cells, called microglia. Their job is to act as housekeepers, clearing away waste and protecting against invaders. But in the presence of amyloid plaques and dying neurons, these microglia become chronically activated. This sustained activation creates a toxic, pro-inflammatory environment. The microglia start spewing out harmful substances that damage and kill even more healthy neurons, creating a vicious cycle of inflammation and neurodegeneration. Then there's the vascular connection. The health of your brain is inextricably linked to the health of its blood vessels. Risk factors for heart disease and stroke, like high blood pressure, diabetes, and high cholesterol, are also major risk factors for Alzheimer's. Chronic high blood pressure can damage the brain's tiny blood vessels, reducing blood flow and depriving brain cells of vital oxygen and nutrients. It can also cause the blood-brain barrier, a protective shield that controls what gets into the brain, to become leaky. A leaky barrier allows harmful substances in and prevents the efficient clearance of toxic waste products, including amyloid, further fueling the disease. A fascinating and increasingly influential theory frames Alzheimer's as a metabolic disease, even calling it type 3 diabetes. This centers on the idea of brain insulin resistance. Insulin in the brain is crucial for neuron survival and memory formation. In Alzheimer's, brain cells can become resistant to insulin's effects, just like muscle cells do in type 2 diabetes. This impairs the brain's ability to use glucose for energy, essentially creating an energy crisis. This impaired insulin signaling has been directly linked to increased amyloid production and tau abnormalities. The link is so strong that people with type 2 diabetes have a significantly higher risk of developing Alzheimer's. This has opened up the exciting possibility of testing whether diabetes drugs can be repurposed to fight the disease. This concept of an energy crisis is also central to the mitochondrial cascade hypothesis. Mitochondria are the power plants inside our cells. This theory suggests that the true root cause of late-onset Alzheimer's is age-related mitochondrial dysfunction. As we age, our mitochondria can become less efficient, leading to a decline in energy production within the neuron. This bioenergetic failure, the theory argues, is the primary trigger that then kicks off all the other pathologies we see: oxidative stress, inflammation, and yes, the accumulation of amyloid beta as a downstream consequence. So after decades of failed trials and a deepening understanding of this incredibly complex biology, where does that leave us? Paradoxically, it has led to one of the most hopeful periods in the history of Alzheimer's research. We have learned critical lessons that are leading to revolutionary new tools. Perhaps the most significant advance has been in how we diagnose the disease. For most of its history, a definitive diagnosis could only be made at autopsy. A clinical diagnosis based on symptoms was often wrong, with up to a quarter of people diagnosed with mild Alzheimer's not actually having the disease's pathology. This has been completely transformed by biomarkers. We can now see the biological signs of the disease in living people, even before symptoms appear. This includes analyzing cerebrospinal fluid from a lumbar puncture, or using advanced PET scans to directly visualize amyloid plaques and tau tangles in the brain. But the real game changer is the arrival of highly accurate blood tests. These tests, which can measure tiny changes in proteins like p-tau217, are beginning to enter clinical use. They promise to make early, accurate diagnosis as accessible, non-invasive, and inexpensive as a routine cholesterol check. This is critical. It allows us to find the right people for clinical trials, and, most importantly, it opens a window for future treatments to be given preventatively, before irreversible damage is done. And on the treatment front, we have finally seen a breakthrough. A new class of drugs, monoclonal antibodies that target amyloid, has finally crossed the finish line. After a controversial start with one drug, two others, lecanemab and donanemab, have shown in large trials that they can successfully remove amyloid plaques from the brain and, for the first time ever, modestly slow the rate of cognitive decline in people with early-stage Alzheimer's. Lecanemab, for instance, slowed decline by 27% over 18 months. Now, we have to be realistic. The benefit is modest, and there's a real debate about how meaningful that delay is for patients. These drugs also carry risks of side effects, including brain swelling or bleeding, and they are incredibly expensive. But their importance cannot be overstated. They are the first treatments ever proven to change the underlying course of the disease. They have proven that the biology of Alzheimer's can be modified, opening the door for a new generation of more effective and safer therapies. The road to a cure is still a marathon, but these breakthroughs are just the beginning. The future of Alzheimer's therapy will almost certainly involve combination treatments, much like we use for cancer or HIV, targeting multiple pathways at once. We'll see anti-amyloid drugs paired with anti-tau therapies, anti-inflammatory agents, and metabolic interventions. But the ultimate goal is not just to treat Alzheimer's, but to prevent it. And the science is clear. We have more power here than we think. Large-scale studies have identified several modifiable risk factors. Managing cardiovascular health, that means controlling blood pressure, diabetes, and obesity, is paramount. Regular physical exercise, a healthy diet like the Mediterranean diet, quitting smoking, and limiting alcohol are all proven to lower dementia risk. And staying mentally active and socially connected throughout life builds what we call a cognitive reserve, making the brain more resilient. The century-long pursuit of an Alzheimer's cure is a story of science at its most determined. It began with the microscopic observation of a peculiar disease and has expanded into a global quest. For decades, the path was shrouded in failure. But now, armed with a deeper understanding of the disease's tangled biology and powerful new tools, the fog is finally beginning to lift. While a definitive cure remains on the horizon, for the millions of families touched by this devastating disease, the dawn of a new, more hopeful era has finally begun.